let's talk about ion selective electrodes and pH meters and how they work. Well, they are designed to respond selectively to a single analyte, at least ideally. That's how they work. Although there's definitely interference issues that you need to be aware of and take into account. Also, these are not redox processes, so you're not reducing or oxidizing any of the species. So but you are using electrochemistry, and that's what drives them to work. So there's several different types of electrodes like this. The glass electrodes and solid-state electrodes are what we're going to be talking about, but then there's liquid-based and also compound electrodes. So I just want you to be aware that there are other varieties. So let's first talk about an ion selective electrode. So here, what we have is an external reference electrode in your analyte solution that goes over through your voltmeter back down to the ion selective electrode body here, which has the internal reference electrode, and it's in contact with the filling solution of a known analyte concentration, which is in equilibrium with this, and then at the end here you have an ion selective electrode membrane. And so let's take a little bit closer look at that membrane. So basically what you have here is this membrane that's full of your analyte in contact with both the filling solution with a known concentration and your solution, your analytes, your unknown solution. And so basically what you have are two interfaces where you have equilibrium trying to be established, where you have your analyte in equilibrium with the membrane, which also has a lot of analyte in it, and then your external solution. So you might have, in order to establish equilibrium, you might have analyte that comes out of the electrode and into solution to establish that equilibrium. And so as a result, you have a charge difference, a difference of the charges at this interface here, and at this interface here, which creates a potential difference that you can measure. So in order for you to have your analyte diffuse from the membrane into solution, you have to have, it has to be a favorable process, so a spontaneous process. So you need a negative delta G. And the the delta G is equal to the delta G of solvation, where you have delta G, the change associated with the solvent of having the analyte desorb from the membrane. So like basically the analyte is going to come from the membrane and it's going to make itself a little spot in, it's going to make itself right at home in the solvent. And so the solvent's like, hey man, what's going on? Like we were hanging out by ourselves, like we don't need you. And so there's a delta G associated with that process, as well as, so then you also have minus RT ln of the concentration of the analyte inside the membrane over the outside of the membrane. So this should look like a familiar equation to you, or at least a familiar type of equation. So then you can work that down, and then you end up with the voltage that you measure, the potential difference, is equal to some kind of constant plus RT over NF times the natural log of the concentration outside, because the concentration of the activity of your analyte in the membrane is going to be constant because you're going to have it be that way. And so that goes into the constant. That's why you can take that away from the equation. All right, so let's just briefly talk about a pH meter, which works on much the same way. So this is a cross-cut through a pH meter. So you have, but I've drawn all of the reference stuff on this side and labeled it on this side, and all of the indicator electrode stuff on this side. So basically what you have for your reference wire is a lot of what we talked about with the standard reference AgCl electrode, where you have some AgCl plus solid, both as a paste connected to the silver wire, as well as in with the KCl. And so then you have a filling solution that's saturated with respect to the AgCl and the KCl. And then a silver wire that's then connected to the voltmeter. So that's sort of your reference, that's your reference electrode taken care of there. So now your indicator electrode is essentially the same thing, So where you have a silver wire coming in, and then some AgCl paste, and then you have a filling solution, or a solution that's saturated with respect to AgCl, but also contains a bunch of protons. And so you have a filling solution that has a known concentration of protons on the inside, and then you have this pH reactive glass. And so let's take a little bit closer look at that. And so on the inside you have your H plus on the surface in equilibrium with the H plus in solution, and that's not going to change. But much like and just like the ion selective electrode, you have hydrated glass as well on the outside, where you have equilibrium being established on the surface on the outside of the solution as well, or with the outer solution, the analyte solution. So in the middle here you have dry glass, on the edges you have hydrated glass, and that's what the H pluses are absorbing and desorbing to. So you have it as equilibrium is established on, well, equilibrium is always established on the inside. As equilibrium is established on the outside, then you have a difference in the surface charge, and that's what you measure on your voltmeter. I also want to mention here that there's a salt bridge between the inner, the indicator electrode and the reference electrode. All right. So there are several sources of error when you're making a pH measurement. You can have the calibration standards that are used are not usually better. They aren't calibrated better than plus or minus 0.01 pH units. Junction potential that we've already talked about is sort of the same, where you or is also a pretty significant unknown, where you have plus or minus usually 0.01 pH units as well. You can also have alkaline error, where you have monovalent cations also competitively sorbing with the H plus at the surface of the glass in the analyte solution. So if you have a lot of sodium particularly, you want to be careful of that, or be aware of that. You can also have acid error, where the pH is, the measured pH is actually higher than the pH of the solution when it's very acidic, because you basically saturate the glass surface with the protons. You can also have issues if you don't equilibrate for long enough. Equilibration requires at least 30 seconds, but can take up to minutes, depending on the buffering of the solution. So a better buffered solution takes a less time to equilibrate. And I can tell you that this is actually, it feels like forever if you have to wait several minutes for your pH to equilibrate, especially late at night. So that's definitely something to be aware of. Also, pH electrodes have to be hydrated just like we do. So you need to hydrate the surfaces before they will absorb protons appropriately and give you a linear response as a function of proton concentration. So also pH that you measure will change as a function of temperature. So you need to calibrate at the same temperature that you're going to be using for your measurements. All right, just the last couple things. A pH meter should respond 59.16 millivolts per pH unit, and that's basically from the Nernst equation. And here the selectivity coefficient, which we sort of touched on the first slide, where these ion selective electrodes and pH electrodes are are designed to only respond to one analyte. But if there's often more than just that analyte in solution, and so you can have competitive binding to the surface. And so the way to measure that is with the selectivity coefficient. So here is the selectivity coefficient K, and it's basically the response to the potential interference divided by the response to the analyte. And so you want a small selectivity coefficient that's better, because if you have a small response to X and a large response to Y, then you'll get a very small K. So that's all.